Good evening, everyone. On behalf of Department of Electronics and Communication Engineering, R.M.D. Engineering College, and my own behalf, I welcome our eminent speaker of session 10, Mr. Saravanakumar, Delivery Head, Thales Avionics, Bangalore, to deliver the session on the topic Recent Trends in VLSI Design and Verification. My heartfelt gratitude for accepting our invitation to share your expertise among us amidst your busy schedule, sir. Thanks for accepting. Now I invite Ms. Srinidhi to introduce our chief guest, speaker of this day. Over to Srinidhi.
Good evening, everyone. It's my pleasure to welcome you all to the session and introduce our esteemed speaker, Mr. Saravanakumar, Senior Engineering Manager at Thales Group, Bengaluru. Mr. Saravanakumar is a highly accomplished engineer leader with over 20 years of experience in VLSI, ASIC, and FPGA design, verification, and hardware validation. With a strong background in aerospace, defense, and telecom domains. He holds an executive management program degree from IIM Bangalore and an MBA from VITS Pilani, showcasing his unique blend of technical expertise and leadership excellence. Currently at Sales Group, he leads design verification and hardware validation teams, collaborating closely with global teams in France. His work focuses on RTL design, e-asset verification, V-loss emulation, and FPGA prototyping, especially for aerospace display systems, adhering to international standards like DO 254 and DO 160. Throughout his career, he has held key technical and managerial roles at leading organizations such as Wipro, United Technologies, HP, CMC, and with his vast global exposure across USA, UK, France, and Sweden, and deep expertise in RTL, System Verilog, VHDL, and hardware validation. Mr. Saravana Kumar brings a wealth of knowledge and international perspective of today's session. We are honored to have him with us today to share his insights and experience in evolving landscape of VLSI and FPGA based system. So I warmly welcome you, sir. The session is over to you. Thank you, sir.
Okay, great. I feel like really honored to share my knowledge. I am basically I am from the kind of industry. So more than 20 plus years of experience and the global experience, specifically in the field of ASIC design and FPGA and emulation. Yeah. So yeah, like here, I want to kind of touch base the recent trends in VLSI, specifically for the design and the verification. I have some slides to share with you. I hope my voice is audible, right?
Yes, sir, your voice is audible.
Okay, that's great. So let me share my screen. So whether my screen is visible for
Yes, sir.
everybody?
Yes, sir.
Okay, that's great. Okay. Yeah. Uh, I have some slides to share and okay on the recent the progress on the VLSI side actually. So I have seen 2 decades of VLSI design and development in different companies, specifically HP, and I work for Intel as a consultant, specifically for the system on chip ASIC designs, and now I am working for a defense and aerospace. So we do the ASIC SoCs and FPGAs for the aerospace and defense applications. So I want to share with you, like from the industry viewpoint, like what, like how we are using. Okay, so yeah, like everybody, knows in this forum about like what is VLSI, like what is ASIC, FPGA. Am I right? So shall I? Okay, yeah. So in that view, see, like in if we think about the olden days, we have vacuum tubes and bulky electronic devices, and kind of gradually the size of the chip is getting reduced. So we started from the small scale integration, then the medium scale integration, and now we call as a VLSI, very large scale integration. And like further we call as a ULSI, ultra large scale integration. That is many semiconductor companies already started to were doing that. So we are talking about now the mantra is basically the artificial intelligence, machine learning, right? And the IoT, so like Internet of Things, right? So this smaller chip, right? We are like this is basically the very like it gives like significance of like for all the like right from the commercial applications to the defense, aerospace and space applications. And also I work with the Space Application Center as well, actually, specifically for the radar imaging satellites. So here, like, I just want to touch base about. So I think everybody, like, here in this forum, everyone knows about the ASIC and the FPGA, like what I assume. So just to touch base, ASIC we call as a application specific IC. So it is mainly for the specific applications. So nowadays, um, we like the typical ASIC contains the CPU, the processor, and the inbuilt buses like ARMBA HB buses. So here in this architecture, you can see the various architecture, like the devices which are connected, like via the AHB. Through the AHB bridge, we can connect multiple, IOs and the IPs. So you can see the various IPs like UART, I square, yes, I squared C, and ADC, CAN bus, and even the Ethernet, gigabit, and LPDDR. So lot of the IOs can be like a lot of IPs can be kind of integrated with the like with the inbuilt bus. And like we like actually in my experience, I started with working with the maximum frequency of 100 megahertz 20 years back, actually. Now we are working for about more than 10 gigahertz, 50 gigahertz. Okay, so we always talk about the gigahertz frequency. So but here in this ASIC, lot of thought process, like went in. Uh, means in our conventional electronic devices, you can see various discrete components. But nowadays, a single chip which contains various devices we can connect, and the inbuilt CPU controls that. So that is fantastic. The idea, and so like as you know well, that the Intel, the company, the semiconductor companies like Intel, the Qualcomm, so they are mainly target for the microprocessor devices, and like various applications like automobiles, commercial applications like laptops and computers, servers, right? So, but the new approach, the NVIDIA. So now the US-based chip maker NVIDIA share market is it went very high actually, because of the AI built-in chip, apart from the conventional graphics processing unit actually. So they are masters in the graphics processing unit, as well as the high-speed video on the image processing chips. But their artificial intelligence-based accelerator, we call as a AI accelerator chip. So that is a big hit for the NVIDIA. And so subsequently, many startups are doing the AI and ML based, ASICs. Also, you can see the FPGAs. It is reconfigurable chip where the basic structure is different from the ASIC. So you can see the CLBs, the configurable logic blocks, and switch matrix and different IOs. And also the kind of interconnect wires. So, like even like I work with the CPLD, the complex, like CPLD, and now we call as a FPGAs, where it has the array of logic elements. And now even the FPGA is acting like a SOC. Like it is basically a SOC, because the ARM processor is a part of FPGA, and with different IO devices, as well as the IPs which are connected so with the chip. And there are plenty of inbuilt resources, logic resources. We can straight away reuse those resources, and we can design, reconfigure. We can configure and reconfigure to any application. But in ASIC, it is fixed, so we cannot reconfigure. So the configurability is the specialty for the FPGA. But there is it has the inbuilt SRAM, which stores all the configurable bits inside the FPGA. So because of this, it is more kind of configurable. And so there are other FPGAs like Antifuse, Actel, like Microsemi, like one-time kind of configurable devices, where it act as, like if we configure in one time, we cannot do the we cannot reconfigure that. So I have specifically worked on that project actually, meant for the space applications, because SRAM is more it is more like highly visible for the microwaves in the space, and so that will impact the bit stream, configurable bit stream inside the SRAM. So because of that, the antifuse is a new technology used in the kind of FPGA, only used for the space grade applications. And for see, like we can't use the FPGA for all the applications. There are commercial grade and defense grade and space grade actually. So depends upon that, like we can select that FPGA. So, but in ASIC it is different. The total architecture is more flexible, and it is up to the user's view. And so the basic thing is, the main thing is why we are using the FPGA. So like as we use low volume, like normally for the aerospace and defense, we use low volume applications. So we use the FPGAs, high-end FPGAs, so which contains SOCs. I mean, like lot of inbuilt, IPs as well as the microprocessor. So nowadays, the concept of like normally in all FPGAs, like SoC based designs, we use ARM processor. ARM is basically the standard processor, the embedded processor. ARM Cortex, 4 or different versions actually. And apart from that, the ARM is connected to the ARMBA bus. ARMBA bus is basically a high-speed bus, and the IOs, the external IOs, are connected through the AHB. So this is the standard architecture of any SoC design, right? So normally this part is now it is changing. So that is the latest trend actually. So many companies, including my company, we are going away from the conventional architecture of like ARM based, ARMBA based architecture to the basically we call as the RISC-V processor, inbuilt RISC-V processor, as well as the network on chip. So the ARMBA AHB is replaced by NOC, network on chip, and the ARM is replaced by RISC-V. So the highlight of RISC-V is a kind of a reduced instruction where we don't need the list of complex instruction set, right? So we can kind of customize for our applications only. And because of this, like we have a flexibility, we have, I mean, like we can scale to many applications, and like it is more flexible for like for the semiconductor company. Slowly, this architecture will also getting advanced for the network on chip and RISC-V based architectures. Okay. Yeah. So coming to the process technology. So we are talking about the artificial intelligence, machine learning. So before we talking about that, we talk about from the process nodes perspective. The process nodes, like I worked for 90 nm technology. It's basically the size of the CMOS. So now the process technology is becoming shrinking. So like 65 28, 7 nm, now 3 nm, and now 2 nanometer. So the Broadcom is working on 2 nanometer technology. You can see how the size of the CMOS, things are changing actually, and so it is the Moore's law. Like we normally talk about the Moore's law, right? So for every year, the number of transistors are kind of getting doubled, right? But now we talk about the silicon and the fin like we normally use the FET based, like CMOS FET based, right? So we slowly migrated from the MOS to FET to FinFET. So FinFET is the technology where the we have the source drain as well as the gate. The gate looks like a fin. So it has more efficiency and low leakage power and scalability, flexibility. But it has some kind of, like we cannot go below 7 nm technology. So if we use the FinFET technology. So now many companies are using GAA. It is a new technology. It is a very latest technology. Gate all around means it is enclosed by gate. The channel width is more, and it is the gates are stacked actually, so the channel width is more, and because of this, we have high efficiency. We can scale up to 2 nanometer technology. So that way, we have we are more flexible in terms of process technology, and smaller nodes, better, speed. Like we talk about speed, right? We can see like now we have like Intel i5, i7 processor, which is 10 cores, and AMD comes with Ryzen, right? Ryzen processor, which is the very efficient processor than the Intel actually. And so like this, semiconductor company, they have done the R&D along with the foundry, and they found the GA is the more efficient way to go with the lesser technology, and low power consumption is very important, and also the speed and scalability, flexibility. So these are the the latest the kind of data, and like even we have migrated from the FinFET to GAA technology actually, and it is more efficient than the FinFET. Okay, so with this, the 2 nanometer technology is slowly, all the high efficient ASICs are built by 2 nanometer. Okay, yeah, so this is the standard VLSI flow. So everybody knows this flow, I think so. I don't want to explain this actually. So like normally, in this VLSI flow, see, there are the difference between the ASIC and the VLSI. So FPGA is basically, it's a straightforward flow where, we don't need the tool at each stage actually, but in ASIC side actually, for each stages we have n number of tools actually. The two major players are one is Cadence and Synopsys, and also Mentor Graphics. They also do the like support the ASIC design flow by EDA tools actually. And in terms of FPGA, we have Xilinx, Intel Altera, and Microsemi are the major players, and we have other vendors also like Lattice. Okay, here, so when we talk about the ASIC flow, okay, so you can see the straightforward flow, right? From the system specification to architecture and then micro architecture, logic design using Verilog, VHDL or system Verilog, okay, and we have to do the DFT, synthesis, okay, and do the DFT and the floor planning. So the physical design starts with the partitioning, floor planning, placement, CTS, clock tree synthesis, and routing, timing closure. And then like the important stage is CTS. So clock tree synthesis. And then like once we do the place and route, so here the two major part, one is the like we have to ensure the functionality has to be met and the timing has to be met actually. So if these two are met, so we can sign off our netlist to the fab, and the fab will generate a sample silicon, chips. So we do the silicon validation in the lab to validate the functionality, and so we do like we have a special lab for doing the silicon validation. Yeah, and then once if all the test cases are okay, then we will sign off our final netlist to the fab actually. And the okay, so this is the common process of the ASIC. So here, so what is the latest, the recent technologies and trends actually? You can see the system specification is the very important one where it keeps on changing based on the kind of customer inputs actually. And here the challenges are, so our objective is to make the chip to work fast, means the speed, low power, and the area should be less. Okay, so these are the three major important things. And also, like we have other physical parameters. The chip should pass all the environmental factors like the process, voltage, temperature. Okay, if the chip is passing with this, with both the functionality, then that is fine. But normally, so we have faced a lot of issues at the designing stage actually, and after the synthesis and DFT and the physical design. So like normally we call the front end design is basically from the system specification to the DFT, and the physical design is the partitioning to the netlist creation. So what's new? Okay, actually, normally, if we go for the ASIC design, actually, okay, so we have to do everything manually. Means like, for example, for the architecture, so we have to do the manual architecture, and so if there is any error, okay, it is very difficult to check. So and we don't have any provision for the code rule check, like whether if we do the coding, there we have to check the coding whether the code will function or not. So at the beginning there is no tool actually, and now the entire flow, right from the system specification to the complete the physical design, is basically fully automated by the EDA vendors. Means that in the semiconductor company, we have fully automated. Like for example, if you want to do the code rule check, so we have linting at the beginning itself. We have we do the power estimation. So there's a tool actually to do the estimation of the power. Okay, we normally use different synapses tools actually. Like specifically, like we have different tools like caliber, fishtail. We different tools like we have. So I will show in separate slides actually. And so the entire flow is fully automated, and there is a CAD team. CAD team means the computer aided design, means the tool team, the EDA tool team will support the kind of engineering team if there is any issues. So they will support us, and so the entire flow is fully automated, and so we will ensure the functionality and there is no bug in the chip. And even there is a small bug, we are able to kind of correct at the wafer level. At the wafer level, we can rectify the issues by working closely with the fabrication, with the fab vendors, right? So this process is called ECO, the engineering change order. So when we raise the engineering change order, so the entire engineering team will work with the fab, and so we will rectify the issues, and so we will close at the wafer level actually. So we don't need to go again the full cycle actually. So if there is a small bug, so if there is a major bug, so the entire chip is scrapped actually. So we have to redo completely. Okay, so yeah, so this is the very latest technology, chiplets, chiplet technology. I want to explain this technology because in industry we started using this technology. Normally in ASIC there will be a separate like we integrate all the system on chip on a single chip. So it means that we have lesser flexibility. So the problem here is, if we use the single substrate or the single substrate, then we are finding more issues actually, and we don't have any flexibility to improve the the chip, I can say efficiency, okay, and the yield. So chiplet is basically a kind of technology where each block, so the entire chip will be kind of classified into different blocks actually. Different blocks, I can say, different, I can functional blocks, and each function blocks have different substrate, or I can say different, yeah, substrate. And so because of this, actually, kind of instead of having the single substrate, we migrated to chiplet based, different substrate based actually, on a single chip of silicon. So the packaging, so here, like, it gives more flexibility to enhance the I can say the kind of effectiveness and the kind of efficiency of the blocks, and we can also improve the speed, and we can also lower the kind of cost. Actually, the cost can be reduced actually because of this. So it is like, like, I can give you one example. So okay, like we are constructing, like the kind of government is constructing the flyover, right? So they used to uh, do the individual blocks, and they will integrate. So here, similarly, the recent new technology, we divide into different functional blocks. These functional blocks have different, I can say, substrate. So, and the entire functional blocks will be packed. So we call as a SIP, system in packaging. So so we will pack that in a single chip actually. So by doing this, it reduces lot of cost actually. So normally, if we go for, I can say, 10 core, like 10 cores or more than 20 cores of chip. So what is, if we make it as a one substrate, so the cost will increase, and in terms of leakage current, it is very difficult to manage with the leakage current actually. But if we go for this chiplet SoC, so it is more flexible. Yeah. So coming to the verification, yeah, in terms of like we have seen about the various kind of the VLSI flow, okay, the design, right? So in terms of verification, like so this is the major area, so normally in conventional design, okay, in conventional design, we use a simple Verilog kind of test bench based, where we write test cases, and we used to verify the functionality of the particular design. So the problem here is the conventional verification methodology will not capture all the issues, all the technical issues actually. So what is yeah, like happening is, because of the verification gap. So because of the gap in the verification, we are foreseeing that there will be ECO at the end actually, to overcome that. So we moved from the test case writing. Directed test means, so we will write the test cases based on the functionality. So just like a kind of test case writing, but if we do the manual approach, so we may miss lot of details. So because of this, so there will be lot of uncovered sections in the design, and so the like we can see some of the kind of coverage gaps. So now the latest the approach is we have moved from the conventional Verilog based test bench or a VSDL based test bench to the system Verilog based UVM, like what we call as a UVM. So UVM is one of the latest verification approach, or the kind of the way of doing the verification. Many companies, like almost I can say 90 percentage of the companies of the semiconductor companies are doing the UVM. So and also the constrained randomized verification is the approach where we follow, where we give the constraints for the randomized variables in the test scenarios, where the tool uh, takes care of I mean, like the approach takes care kind of takes care of all the cases, actually, corner cases, as well as the normal cases. Okay, so that way, so we will avoid any manual intervention of the verification. And coming to the emulation, like when I talk about emulation, uh, see, like we cannot do the 100% verification for the SOC based, the complex SOC based systems, because it has the processor, and it has the on chip uh, like interconnect devices. So it is very difficult to achieve the full-fledged verification. So, and also the verification takes more time, actually. It consumes more time. So because of that,
The resource person is having some network issue, so he'll join us shortly. Kindly bear with us.
Hello.
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 Yes, sir. We can hear you, sir.
Yeah, yeah. Okay. So shall we?
Sir, we can hear you, sir.
Continue?
Yes, sir.
Hello.
Yes, sir.
Yeah, yeah. So
Yeah.
shall we continue?
Yes, sir. Yes, sir.
Okay. Sorry, like I cannot in my laptop. Some problem is there. So I cannot share my screen actually.
Okay, sir. No issues. Sinaj,
Yeah.
can we share the screen, sir? Suppose if you are able to share your PPT, is it okay for you, or you can just take it in the oral manner? It's up to you, sir.
Yeah, I can take it in the oral manner.
Sure, sir.
Yeah, 1 second. I'm just yeah, yeah. Okay. So we have seen about the verification, right? And emulation. Okay. So what are the okay kind of EDA tools like we are using, like as we know, Synopsys Cadence. So and Meta Graphics. So apart from this, so we have the other things like emulation side actually. So we use a Veloci emulator and Zebu from Synopsys. So we have like lot of kind of emulator, and yeah. So coming to the okay kind of artificial the like how we can apply the AI. So like normally if you see the flow, like actually the tool can also help us in terms of it will review the reports actually and help us to and also gives the feedback. Okay, so where the issue here is and also uh, like um, we have various the kind of EDA for example the AI is embedded in some of the EDA, like for example the Synapsys DSO dot AI, so where it is mainly used for the space optimization and specifically focus on the area speed and in terms of impact actually it improves the kind of efficiency and like we have Karen's tool. So where this tool is specifically it optimizes the kind of like a physical side part actually, and also it cuts the like the human effort actually. Like we are spending more time on the kind of in terms of like finding the errors and from the log file, like we are do like we are spending more time. Okay, so here these tools which help us to uh, it will find out and it will help us to see how we can fix the issues faster and also like for example the AI tools will generate the code itself actually, but so we have to still optimize the code for the kind of efficient usage. Still the AI is not fully stable enough actually, so still the the human effort is needed uh, to make the source code more stable and also we have a lot of things like for example in terms of IP yeah, like IP design and the error log kind of analysis, this tool is very useful actually. So these are the some samples of the AI. And in terms of verification, how the AI is being used. Okay, so it that the tool will give the structure of the system Verilog UVM framework, and so we don't need to generate from scratch. So this will cut down the verification cycle actually, where the main effort goes into building the verification environment and the UVM components in the verification side actually. So like this, it cut downs in kind of establishing the SVUVM, verification, uh, like I can say framework. And also it also help us in doing the fast code coverage kind of analysis, where we are spending more time in doing the kind of code coverage analysis actually, where so we have to do the kind of analysis in the logs and sync up with the kind of same team. So but this AI tool will till exactly which part of the code is not covered actually, and it also gives the input for the verification engineer how to write the corner cases to fully cover the verification. Okay, and also this AI is also used for the assertions, like it also we can use the kind of assertions in the verification, so which can be obtained from the AI. And also, in terms of test cases, actually, normally we are using the manual approach, the of writing test cases, right? So this AI, like actually the main issue here is when we use the AI for the complete verification, like we have to upload the source code, the design source code. But like for the AI, we need a separate cloud actually, where it should be a separate, like secured one actually. So once if we have a secured server in place and cloud in place, so we can deploy that AI and we can upload our code, and the AI will, so like it will so definitely help us in terms of cutting down the effort of writing the test cases, the functional test cases, for the I can say, like if we do the verification for about say 5 months actually, so it will cut down by approximately, like we can complete this the verification by uh, uh, half of the um, yeah, effort actually. So likewise, here the major effort goes in the framework, the writing the verification framework, and second thing is writing the scenarios and building the UVM components. So these are the core areas where we are spending more time actually. And so if we use the AI more effectively, we can kind of cut down the verification life cycle by half. So we have used this AI in our company actually, and like more specifically for the code coverage kind of analysis. So we are able to successfully improve the kind of coverage actually, and so it cut down the our verification cycle. So but so we cannot fully rely on the AI. So there should be some kind of mix and match of the human intervention and the AI. So will help us in terms of improving the design and the verification life cycle. So okay, in terms of the future and the okay, like what we can see is, definitely all the tool companies are migrating to the AI based approach actually, the tools where the tool is smart enough to help us to do some kind of analysis of all the log reports and the reports generated at the each stage of the design cycle as well as the verification cycle. And also it help us in kind of cutting down the human effort actually, where the huge number of test cases are required, or the like specifically I can give you in terms of a design for the front end part. Actually, after a synthesis, so we have to do like a lot of analysis part. So this analysis part, like we have to fix, like it will go for many iterations. So to fix all the violations, so we have to do like lot of kind of iterations actually, and we have to fine tune the constraints. So this AI part will help us how to give the right constraints based on the design flow actually, as well as it help us. It gives the like inputs actually, how and like so that we can definitely cut down the human effort in terms of kind of analysis and bug fixing. So this will definitely a breakthrough in the semiconductor field actually. So right now, many semiconductor companies are like have started implementing the AI slowly, but not fully. Step by step, they are kind of implementing. And nowadays, the AI accelerators are coming in. So while this is the kind of the like so this is the future actually, and the kind of quantum computing is the very important part where definitely the see the AI and the kind of quantum computing will take the semiconductor field to the next level actually. And there are lot of skilled engineers needed in those areas, like specifically in the AI plus the semiconductor, the kind of logic, RTL design verification side actually. So if this mix and match uh, happens, so definitely if the kind of if we have the skilled, so if we reskill in terms of AI as well as the complete flow, so definitely the future of the semiconductor is a very vast, and we have a very good future. So with this, I can close the session, and if you have any kind of questions, so we can discuss. Hello?
Yes, sir. Just a minute, sir.
Yeah. Okay. I think no one has a questions actually. I'm extremely sorry. My network as a issue actually. So I have to kind of convey this orally. I so really appreciate you for this session, and hope this session thing is very useful for you.
Thank you so much, sir, for sharing your expertise with us. No, it's not an issue. Sometimes it happens here. Now I invite Ms. Senthil Priya to propose the vote of thanks for this session 10. Vote to Senthil Priya.
Very good evening to everyone. It's my privilege to propose the vote of thanks for today's insightful session. On behalf of R.M.D. Engineering College and Department of ECE, I extend our sincere gratitude to our distinguished resource person, Mr. Saravanakumar Ranganathan, Senior Engineering Manager, Thales Group, Bangalore, for sharing his rich expertise and industrial perspectives with us. Sir, you have given an excellent effort to deliver the session smoothly and sharing valuable insights on modern design and verification technique. Thank you very much, sir, for taking the time from your busy schedule to enlighten with us with your knowledge and experience. Thank you so much, sir.
Yeah, welcome. Okay. See you then. Okay, bye.
Thank you so much, sir.
Yeah, yeah. Welcome. Okay, bye. See you.
Bye, sir. Dear participants, thank you all for your participation in day 5 of AICT Atal FDP. So tomorrow is the last session. So our session will begin by 2 o'clock. So kindly join by 2 o'clock. Thank you so much. Have a nice day.